Still in the topic of momentum, energy, work energy, and power, we're now looking at the energy side. So we're going to define work done, and this is the one equation that gets forgotten. I don't know if the English there is right, but the work done on an object is the product of the displacement and component of the force parallel to the displacement. So this is often in a multiple choice question. If I'm carrying something and I'm holding a tray, so I'm carrying coffee, and I am carrying that coffee in this direction. You need to remember that I am doing work only on the cup in that direction. If there's no work done on that cup in that direction because it's not moving, so I have to look at the force, what force is applied on the cup, and the force is applied upwards on that cup for me to hold it up. But I'm moving this way. So by walking forward, I'm actually not doing any work on that cup. So if I say work is equal to the force times by the distance, so Fs or F delta x, really doesn't matter what you would like to use. Yeah, I often use F delta x because it's a displacement. But here, there's no displacement in this direction. So if you're thinking of the work done on the cup in this direction, there's actually nothing. I'm holding it in one position, not up and down, but if I'm moving it forward, there's work done in that direction. So please, no force, if there's no work done in the direction of the force, then there's no work done. Or if there's no displacement in the direction of the force, then there is no work done. Now, please also remember that work is a scalar, and for that reason, this equation is often used in the wrong way. So I would rather you stay away from this equation and remember that your force is the vector. Go and calculate your force first, and then all you have to do, because the force has the direction, and calculate your total force first. So the work is equal to the force times by the change in displacement or change in position. So if you know the force and the direction of the force, you know the work done in that direction. So please don't go and talk about work in specific directions because that doesn't happen. It tells you here that work is a scalar. Please, that's important. So when you use this equation, actually, if the work is done by an engine, you need to remember that force must be the force of the engine. If the work is the total work done, then the force must be the net force. So if I want to say the work done by friction, then I'm also going to say, okay, that's the force of friction times by the distance that the friction was applied. So you can always go and put little subscripts. Just remember that the work done by that specific force, you have to work with the size of that specific force. Now, where I mean this is forgotten is often in the work energy theorem. So if you look at the work energy theorem, it states that the change in kinetic energy, so if you look at it here, it says the work done by a net force on an object. Now, if you look at your information sheet, you'll see W is Fs and it's not W net. So that equation has changed, luckily, because work net, you're putting directions there that shouldn't be there. So when you get that equation, again, here on your information sheet, I want you to go and make a change. Because you know the work is equal to the force times by the distance. I'm going to just use F delta x here. So work is F delta x. But now here they tell you that the work done by the net force is equal to the change in kinetic energy. So not the net work, the work done by the net force, so F net, is equal to the change in kinetic energy. So you need to think firstly, again, as a Newton, what is my net force? Once you have your net force and you have your distance, it becomes easy because you can work out the change in kinetic energy. So this is often where something is moving and then it stops. So you're moving due to friction, or you're stopping due to friction. You came down a hill and there the object is moving, and then over 10 meters it's going to stop. So you have the kinetic energy here. So it has kinetic energy here and it has zero kinetic energy here. So if you look at the work energy theorem, and they're now going to ask you, for instance, for the frictional force, then you know the work done to make this stop was the frictional force. There's no other forces. So you can say that the frictional force is the net force. So the frictional force times by the distance is equal to the change in kinetic energy. And remember, any change is always final minus initial. So in this case, you're going to have 0 minus something, and you're going to end up with a negative answer. Yes, that is right. I know energy is a scalar, but it's negative because this force is acting against the direction of motion because it's making the object stop. So think about the energies being positive and negative logically, because here you'll see work done on an object is positive. So if it had an engine, it would speed up, and then this answer would be positive. If there's friction that makes it slow down, you will end up with negative work. It just means that energy is lost by the system. It doesn't mean that it now has a direction. So please always final minus initial, and if it's negative, you know the object has lost energy, and if it's positive, then the object has gained energy. So you can see that's what it says here again. Kinetic energy increases when the force is in the same direction as the distance or the displacement. And kinetic energy decrease when the force is in the opposite direction. So for our one here, because it was stopping, the force is against the direction of motion or in the opposite direction to the displacement. So these two, please see them as one. And when you get your information sheet here, so W equals Fx or W equals F delta X, please go and write here that that is equal to the change in Ek. Or what you need to go and do is where you see this equation where it says W net equals change in Ek. Remember, you're not allowed to say the net work done. You have to then go and put another bit in here. So I would love you to go and add this on your information sheet. It's not the net work, it's the work done by the net force. So put in here F net delta X, because these things are all equal and these things are all equal if it is the net force. So here it must still be net force, will be the change in Ek. So it would be better if you don't do it at the top, but you do it at the bottom at the work energy theorem. Here you can also use this then as a crib note for your work energy theorem, because it says that the work done by the net force, not network, work done by the net force is equal to the change in kinetic energy. Then if we look at mechanical energy, remember mechanical energy is the sum of your potential energy and your kinetic energy. So you need to remember that gravitational potential energy is mgh, and that is due to the position. Kinetic energy is half mv squared, and that is due to an object's motion. That you know. Mechanical energy is the sum of those, but remember that it's at a specific point. So the sum of the potential and kinetic energy at a specific point. So this energy, this mechanical energy, cannot be destroyed or created, and that is the conservation of energy, because we can just take this energy and convert it into other forms. Now, when we say it's an isolated system, this energy is not converted into other forms, and that is to say that the potential energy and the kinetic energy, the sum of those at any position, position 1, will be equal to the sum of those at any other position if it is an isolated system. So they say here, in the absence of air resistance or any external forces. Remember that you can also just change into saying in an isolated system, because that's exactly what an isolated system is. So it's only the potential and kinetic energy that we look at. So these questions typically is when something falls down from a height and there's no frictional forces, then you can use this. So if an object is falling from here to here, you know that you have EP at the top. You don't have any EK, so plus 0. You have EK maximum at the bottom plus 0, because at the bottom, as it hits the ground, potential energy would be 0. So you can say EK plus EP at the top is going to be equal to EP plus EK at the bottom. You can fill in your values and you can calculate whatever they're asking. Normally they're asking you for or often they ask you for the velocity that hits the ground, or they give you the velocity and they ask you for the height there. This is also for objects sliding down surfaces. If there's no friction, you can say that the mechanical energy here at the top is equal to the mechanical energy here at the bottom if no energy is gained or lost. And that is where we come to this last little bit here, where it says conservation of energy, where there is actually something else acting on the object. So that is important. Now, here, before we get to power, I'm actually going to just skip a page that I can tell you here. So if it is an isolated system, so, for instance, the example where you're sliding down, there's no friction. If it is isolated, then we can say, okay, EP plus EK at position 1, so here at position 1, must be equal to EP plus EK at position 2. Now, you just fill in your values. You go mgh for potential energy, you go half mv squared for kinetic energy, and the same on the other side. Normally one value is given. Please remember that also in a case like this, it's normally the same object. So I'm just going to fill it in to show you quickly, because you can simplify the maths, and sometimes they don't give you the mass and you think there's information missing, but actually there's not, because this is just going to be half mv squared again. Now, because it's the same object sliding down this hill, the masses are constant, and therefore the masses can be cancelled out. So this is then at position 2. So just remember that if they don't give you the mass, if it's an isolated system, it doesn't matter. Now, if it's not isolated, there are two things that can be happening. You can either gain energy because work done on the object. Now remember, not force. Work is energy. So if it's not isolated, you can say, all right, I start here at the top and I end here at the bottom still, but now there's friction. So now you need to think, okay, I still have EP plus EK at the top. I still have EP plus EK at the bottom. But has it gained energy because of friction, or did it lose energy because of friction? So you started with a certain amount of mechanical energy, but you're not going to end with it, because some of it is work done against friction. And if work is done by the object against something else, then remember it's negative work, because we are losing energy. So minus work done against friction. And then super important, please remember that this is still equal. So work done by friction is still equal to F friction times by the distance. Like I said before, this equation is forgotten way too often. So to get the work done, you're going to just say the frictional force times by the distance. So if it's not isolated and you're losing energy, you're doing the same type of calculation, but you're going to minus with the work against friction. The other scenario would be if it's gaining energy. So now, if this object had an engine while it's sliding down, or we can make it go up if you want to, then it's got an engine. And so that means it's gaining energy from that engine. The system has an extra force acting on it, which is the engine. But we don't put force in this equation. So again, we're going to say EP plus EK, but now we're going to say plus the work done by the engine is equal to EP plus EK. When we end. So please just think about it nicely. Is work done on the system, or is work done by the system? If work is done on the system, you're going to say plus the work done on the system. If work is done by the system, you're going to subtract it. And then again, this would be the work done by the engine would be equal to the force of the engine times by the distance that it's acting. And we're not going to put a direction in the work. Remember, you work out the force by adding in the directions because your force is your vector. Last little bit. Power. Power is just the simplest thing that is also not looked at in enough detail. Power is the work done in a specific time. So the definition, again, if you've got a T at the bottom of the line, it's the rate of work done or the rate of energy transfer. And here you need to remember that work is equal to energy transferred, is all energy, and it's all measured in joules. So power then, because if you look at the unit for power, it will be joules over seconds. So the unit there is going to be joules per second, but we gave it another name and we called it a watt. Now, please remember that these are equivalent units, and they often ask this in a multiple choice question. Actually, for all the sections, you must know how units are derived. So then if we look at this equation, the work over time, now you know that the work is equal to force times by distance over time. Now, this you must be very careful for because it does give you delta x over t or s over t, does give you velocity. But this is only ever when this velocity is constant. I wish I had a shocking color. This velocity must be constant. If it's not constant, you cannot use this equation. So if a force causes an object to move at a constant speed only, you can use that equation there. Otherwise, you must go back and work out the work done divided by the time, and then you get your power. Then just remember the efficiency question is often not in this section. They like asking it in electricity section and in the electrodynamics section for motors. But just remember that efficiency is the power out. It's what you're getting out of the motor times by over what you're getting in, we're giving into the motor. So that's why it's often asked in the electricity section, because if they say a motor is rated 200 watts, it basically means the electricity, so power is equal to voltage times by current, is supposed to give you 200 watts. So that's your input that you get, or that the motor is supposed to give you. But now it goes and lifts something up only to there in a certain time, and you go and work out power is equal to work over time, and you only get 150 watts out. So then you will say 150 over 200 times by 100. If you get an answer that is bigger than 100, you must know that you've done something wrong, because no motor can be more than 100% efficient. So then it would lead you to the fact that you actually swapped your values around. Powers should be easy, so please don't miss marks because you're interpreting these questions wrong. And that's it.